We will first start with the book. I think all of you can also see the book now in front of your screens.
Yes, sir. Visible.
Thank you. So if you remember in the last lecture, we were actually discussing LMUT, Transmit Diversity Scheme, and we finally came out to discuss the space-time code criteria for the determinant criteria for space-time code design. And after a lot of complicated mathematics, we were able to show that the probability of confusing a space-time code XA with XB is equal to this factor, where you can see these are actually constants, but they show the diversity gain of L. But the main thing is that the probability of error is determined by the determinant of the product of the differences between the two code words. And you can see that lower the value of this determinant, higher, because this determinant is present in the denominator, so higher will be the value of this fraction, and hence the error will be bounded by the smallest value of this determinant. So you can say that the coding gain is determined by the minimum of this determinant over all code word pairs, and this minimum and this determination is called the determinant criteria. I was trying to, just as a bit of discussion, I was trying to upload one recorded lecture, and I found that it was taking a lot of time. If I could tell you, I tried 4 or 5 times, but of 235 or of 275 megabits, so it takes a lot of time. Other than that, else, you can see that most of the lectures are uploaded. Yes, what are you saying?
सर आप गूगल ड्राइव पे शेयर कर दिया करें.
अच्छा, गूगल ड्राइव पे.
हाँ, से हम खुद ही डाउनलोड कर लिया करें.
Right. Google Drive पे the main problem is that in uploading, I am able to download from MS Stream in no time, but in order to upload it, it becomes very difficult. That is the problem. Even, you know, I was actually trying, if I could show you, I've tried about 4 or 5 times to upload this lecture, the last lecture, and every time I have failed. It is still updating. So it has actually updated 202 megabits out of 245 megabits. It is doing, inshallah, in a few minutes it will be updated. So it is better that we will use this streams, so that MS Stream, so that we are synchronized. Umar Idris. So Umar Idris is not in the class. I think he has to. All right. All right. So I don't know whether I should admit him or not. So coming back to the lecture. All right, everyone turn off their videos and audios. All right, so we come back to the lecture here. And so I was telling you that this is the main criteria. Okay? That the minimum value will determine the coding gain. The minimum value of this data. Yes.
Kindly sir, 5 या 10 मिनट ना वेट कर लिया करें. वो 6 बजे पिछला लेक्चर खत्म होता है, तो अगले नमाज का टाइम मिल जाया करे ना सर को.
असर का टाइम तो काफ़ी पहले हो जाता है, वैसे के टाइम 5:30 भी। वैसे मैंने यही बताया कि असर का
सर
टाइम
हमारा
तो
लेक्चर 6 बजे
हाँ।
खत्म होता
हाँ आप सही कह रहे हैं, आपका 6 बजे लेक्चर ख़त्म होता है, मगर भी असर के टाइम में सच्ची बात है काफ़ी पहले से स्टार्ट हो जाता है। वो तो हम लोग ये 2 साल के चक्कर में ना लेट हो जाते हैं। वैसे तो असर का आप देखें 4 बजे के करीब शुरू रहता है असर का। वैसे सुनहदीस के मुताबिक ना 1 साल पे ही स्टार्ट हो जाता है। तो अगर आप वो कोई वेबसाइट वगैरह में ये स्टैंडर्ड टाइम देख लें ना, एक तो ये मतलब एक ही टाइम में 2 साल वाला जो इमाम हनीफा वाला, बाकी अगर आप देख लें ज़्यादा वो स्ट्रेंथ भी है उसके उनकी दलील में ना, बाकी तमाम आइमा की। तो असर का टाइम तो 4 बजे हो जाता है। अगर ऐसी प्रॉब्लम तो 4 बजे के बाद भी पढ़ सकता है असर। तो वो आप
ओके सर।
देख लें, वो एल हदीस टाइम भी देख सकते हैं, वो भी तो जल्दी शुरू हो जाता है। इस तरह के मसले हो तो बंदा इस तरह से मसले हैंडल कर ले। अब मसला है कि हमारे पास मगरिब तक टाइम बताएं कितना है, 7:12 पे मगरिब है, तो वो फिर वो मगरिब जाती है। इसमें है कि असर अगर आप देख रहे हैं क्लास में प्रॉब्लम आई तो बंदा थोड़ा पहले पढ़ ले और एडजस्ट कर ले, क्योंकि असर का टाइम ना 1 साल पे स्टार्ट हो जाता है। तो एल हदीस टाइम देख लें या किसी वेबसाइट से देख लें टाइमिंग, तो 4 बजे स्टार्ट होती है सर। ठीक है, तो होप इज दिस सॉल्व्स द प्रॉब्लम। अच्छा, सो कमिंग बैक टू द लेक्चर, मैं क्या कह रहा था? Oh yes, देखिए we did a very very important mathematical derivation last time. That the probability of confusing two different space-time codes is actually given as follows. ठीक है, मतलब कि two the scheme is same. For example, we are applying LMUT, we are applying BPSK scheme on LMUT, then on LMUT space-time code, then the probability of confusing one code with the other code is given as follows. Okay, so this was done. Now he's further explaining this, that what will happen if I apply transmit diversity code. Remember what is the difference between transmit diversity and LMUT? In LMUT you were actually sending two different symbols in the same time slot. This is LMUT. This is you, if I have told you, this columns represents time symbols and rows they represent antenna. So in one time symbol you were sending two different symbols from two different antennas. But if you remember, what happens simply is what happens in क्या कहते हैं उसको, in transmit diversity, when transmit diversity is applied to repetition scheme, is that you have to repeat your same transmit diversity, because it does not have the capability of utilizing the spatial dimension, because transmit diversity schemes, they were just devised for time diversity. So how can we do that? We say, all right, send the first code here and then send its replica in another channel. So that is possible if I apply, if I, when I'm sending its first version, I will keep the other silent, and I send its second copy, then I will keep the first silent. In this way, in two different time slots, I will have two different channel coefficients, as was requirement of time diversity. So this is the same thing. If you could observe, that he's saying that if I am sending transmit diversity codes, then you can see that my code will be along the diagonal. Space-time code matrices are along the diagonal, and in that case, you can very well see that this between it will just come out to be DL square, because in that case, you know, XA minus XB will be just the difference between the two codes. There's a difference between the two codes. All right. So, and if I say one and the second, this will again become DL squared, DL mod square. The same mod square that we actually found for the 3.68 criteria for time diversity. If you remember, in time diversity, it was the same equation, but this is more general. And here you could see it was something like this. And what was it? This was actually the difference between the two code words. So here you will be again taking the determinant, which will be again the diagonal, and the difference between the diagonal will be actually giving you the same thing, provided you are sending transmit diversity over the space time scheme. This was actually. Now let us try to compare. Again, I have told you mathematics is, a lot of mathematics is missing. So I will be showing you my notes so that you get a good practice of applying any, first of all, any modulation scheme over LMOT scheme, and then finding the determinant criteria. So let us go and look at our mathematics part. All right. So I am saying that I have a LMOT scheme. Okay, the same thing you saw, you know, U1, U2, and you minus U2 and then the U2 conjugate. Same thing here. I am applying this LMOT scheme. This one, U1, U2 minus U2 conjugate, U1 conjugate. Please remember this. Let us try to apply. Now I am saying that I yes.
स्क्रीन शेयर कर सर, ये बुक की स्क्रीन शेयर हो रही है, नोट्स की नहीं हो रही सर, वो शेयर करना है.
Notes, you are not at this point. Are you seeing these? Can you see for LMOT scheme my writing?
Yes sir, abhi
these are the notes. Because you know I have used CAM scanner, so the notes they are converted to PDF file. So there you do not have to share it extra. Just have to click because they are both PDF, the book as well as the lecture notes. All right, these are the lecture notes. So for LMOT scheme, okay, with BPSK symbols or BPSK symbol code words. Now what are the BPSK symbol? We know it is, you know, minus A plus A. Let us say here we say A is equal to 1. So I have actually, what are the BPSK symbols? If I am sending 2 at a time, so I can send 1 1, 1 minus 1, minus 1 1, or minus 1 minus 1. These are the only 4 different scenarios I have. All right, because I have 2 symbols 2 to the power 2, I have 4 different combinations. Now what will be the corresponding LMOT code for any two BSK symbols? So you know this will be U1, U2, this will be U2 conjugate minus U2 conjugate, this will be U1 conjugate. Because they are real, they will look like this. In this way you will find the relevant code words for every combination of BPSK symbols. So in this way you can find these 4 symbols. Everyone is understanding how I found these 4 code words? If there is any difficulty, please ask now. Then there will be no more repetition. All right, very good. Thank you. Acha. Now, one thing is normalization. Now, please remember that when we are driving this mathematics, we said for convenience, we normalize the code words so that the average energy per symbol time is 1. This is very good. Hence, SNR is 1 over n naught. Now for BPSK, it was actually a square over n naught. But I want to make it 1 over n naught. Remember this thing. Remember, I can say actually, you know, signal energy is signal power over noise power. But I can say it is average energy per symbol. Actually, it was average power. But when I say average energy per symbol, it becomes average power. All right. So both are the same thing, no problem. Average energy per time or power, same thing. Now, how this important thing is to how I will need to apply here. Remember, so I have, because many students they get confused this time, I have made these notes so that there is no confusion. Now, average energy per symbol time or average power for BPSK with plus A minus A symbols is A square n naught. Everyone knows it is A square n naught, no problem. All right. Now, but here the difference is that in LMOT scheme we are sending 2 symbols. We are not sending 1 symbol. And we want to normalize that the total energy sent in 1 symbol is 1. Now, if I send 2 symbols, BPSK symbols, then you can see that my energy will be 2A square over n naught. But my signal noise ratio will be 2A square over n naught. Or energy will be 2A square if I do not take this n naught. I took this n naught to be, you know, consistent with the book. No problem if you don't want to put. Main thing is to normalize energy. N naught remains N naught. Now, now how can I normalize? I want to make this 1. So what I will do? I will divide 2a square by 2a square. In that case, I will have 1 over N naught, which I want. So I need to divide my average powers or energy per sample time by 2a square. Now here the problem is that in this case, which one example I am discussing, I am saying all I take a is equal to 1 because all our symbols were 1, 1, 1 minus 1. So a was equal to 1. So here a is equal to 1. So for power I need to normalize by 1 over 2 or for average energy per sample time. But for amplitude I need to divide by 1 over under root 2. Very important point. Many students they make mistake. So I need to divide by 1 over under root 2. All the amplitudes of all the BPSK symbols which are present in the LMOT code word. Now no problem. I have just divided all of them by under root 2. In this way, I am getting all my normalized code words. Are everyone understanding how I got these 4 code words? Normalized code words?
Yes, sir, it's all right.
Let us go further. Let's say, yeah, I took, notes were straight, but when Cam Scanner took the picture, I don't know, it made it, these in wavy form. So maybe I didn't took the right picture, but still it is understandable. I use pen. Many teachers are telling me, the one teacher is telling me actually that please use pencil so that you can rub it. But I think no problem if I have put a cross mark. I can also make a mistake. There's no problem making mistake in making a lecture. So main thing is that it is visible. With pencil, I've noticed it is not that visible. Then if I put a pencil and then I, double mark it by a pen, it will take again time. So I use pencil. If there is some crossing, you can just see that anyone can make mistake. Now we have found the code words, but what is the determinant criteria? If you could see in our book, the criteria that we need to find is this thing, determinant of xa minus xb, xa minus xb. Now please see how many code words do I have? I have 4 code words. So if I want to find the minimum of the difference, I have to take the difference between 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, and 3 and 4. This total comes to be 6 different differences that I have to take. And then I will to multiply the difference with its Hermitian, take the determinant, and then I can see what is the minimum determinant criteria or the minimum value, and that will determine the overall coding gain or the order of the error. So so I have taken XA1 and XA2, so it is a little bit wavy, slanted. This is XA1, this was XA2. All right, you can see from here was XA1 and this was XA2. XA1 and XA2. So I take the difference XA minus XB. So 1 over under root is common. I can take it outside, so it is very easy to go. 1 minus 1 is 0. This becomes minus 2. This becomes 1 plus 1, 2, and like this. Then I take its Hermitian. So in the Hermitian there is no conjugate, so no problem. Just I take the transpose. So transpose, the column becomes a row, the rows becomes a column. So this remains the same, and this comes here, this goes there. This comes out to be like this. Then I multiply the difference with its Hermitian. So multiply the difference with its Hermitian. So I will take its row, multiply with its column. So I get 4. This is 0. A mistake by me, which I have crossed. 0, 0. This becomes 4. So 2, 2. This will become 2. 2 goes inside. This becomes 2, 2. So this becomes determinant. Now please see one very important point. Many students again make many mistakes. So I don't want you to make mistakes. All right. So before you calculate the determinant, make sure all these constants are taken inside. Don't keep these constants outside, find the determinant and then divide by. Determinant is of the whole of this matrix. So solve total, then take determinant. Solve total, then take determinant. This is the procedure. So 2, 2. So you can see determinant is very simple. It is 4 minus 0. It is just 4. So I got 4. This is the determinant which I am getting 4. Now let us do another example. Here I am doing 1 with 4. I'm not doing 1 with 3. You can do yourself. I am doing 1 with 4. So this is 1. This was my 4. Again, take the difference. Then you can calculate the difference with its Hermitian. And finally, you will be able to find the product. Then take its determinant. But I have told you, so before taking the determinant, take this to inside so that you have a matrix. Then find its determinant and you will get 16. You can see one way I am getting 16 because you could see that here the difference is greater, 16, while here the code word difference was 4. Now if I just ask you why this is happening, because you can see that 1 and 2, they were actually corresponding to symbols in which case there was only one difference. But in 1 and 4, you can see the difference is greater because 1 is going -1 and 2 is going -1. That is why the difference is greater. All right. So that is why I get this 16. But you have to find the differences between all the code words. So you need to find also between 1 and 3, its conjugate, then 2 and 3 conjugate, 2 and 4, then its conjugate, and 3 and 4 conjugate. So all the combinations are need to be taken, and then you can find the determinants, the determinant criteria. Then the minimum determinant criteria will determine the coding gain or the overall error probability of or the order by which the error probability would be governed. Now this is one thing. So if I ask you what is the minimum criteria of BPSK symbols over LMOT scheme, what will be your answer? You will say 4, because I have done the rest. I have not shown. You should do yourselves. It comes out to be 4. All right. So you will say it is 4. Now let us try to apply PALM or pen. Now remember, so here as a book wants to compare, we are just following the book here. So you can see that we are using repetition scheme with 4 PAM. So we are comparing LMOT with the repetition 4 PAM. All right. So we are not taking PAM onto LMOT, but rather we are taking repetition scheme. Now repetition scheme was a transmit diversity scheme. How transmit diversity? Repetition scheme, time diversity scheme. So in time diversity scheme, you don't have antennas. How could I apply a time diversity scheme over a space-time codes or over antennas? This was the answer. Repetition scheme or any transmit or any time diversity scheme can be applied or can be generalized in form of a space-time code as follows, where you are not utilizing these symbols because it has no double antennas. It does not, its code does not work for 2 antennas. It's just 1 antenna. So what I was saying, so I will apply my repetition scheme with 4 PAM, all right. With 4 PAM symbols and try to find the minimum determinant criteria. So again, these nodes will be uploaded. So first of all, I make up my symbols. So my symbols, 4 PAM are as follows. Then I form with these PAM symbols, I form the LMOT code words. So you can see there will be 4 code words because remember that 3B has to be sent with 3B. It is repetition scheme. And these are 0. This is not PAM over LMOT scheme. All right. So I have 4 code words. Now I need to normalize. But remember, its normalization is a bit different as compared to normalization over BPSK. Why? Because here the average power is 5B square. So to normalize, I have to divide powers by 5B square, but amplitudes by under root 5B square. In other words, I have to divide the symbols by under root 5. Divide all the code words by under root 5. Hence, you will get these normalized. You will be getting these normalized code words. All right. You will be getting these normalized code words. So again, I try to apply the determinant criteria. So I choose XA1, XA2. It is my wish. I have to, when if it is asked in question, try all the combination. You have to try all the combination. If the question says all intelligently chose 2 code words, you have to choose intelligent. You can see difference between this and this will be greater because this is minus C, this is B. Here also much greater difference, but difference between this and this will be less because this is the next consecutive symbol, minus 3B, minus B. They are the most near. So I will try to find here so that I get the minimum criteria. Minimum will come the denominator, and it will be able to, it will be able to maximize our ratio. So I apply this xa minus xa2. So this is my xa1, this is my xa2. Again, I take under root 5 outside. This was minus 3b. This was my, but you know, bb cancels because I have divided by under root 5b. And in this way, this comes out to be like this. I can take 5 common and I can just add them. They become like this. So I found the difference. I found the difference. Now I will take the product of the difference with the difference conjugate. It will be like this. This is h. So you cannot see it, but this is h. And then I will, do multiplication 1 over 5. So before I find the determinant criteria, I need to take this 5 inside like this. So now I can apply the determinant criteria. This will be 16 over 25. So actually this is the minimum. Now you can find all the other differences. So the minimum comes out to be 16 over 25. So now what I have seen that, let us say that I keep the minimum distance same. You know, minimum distance here between a plus a and minus for BPSK was 2a. Here it is also minus 3b minus b. It is 2b. If I keep the minimum distance same between the two schemes, all right, then in that case you can very well see that the gain of the coding gain, because you can see this is 16 over 25 and that is 4, right? 16 over 25 and that is 4. All right, so you know that will be actually 1 over 4 and that will be 1 over 16 over 25. All right, so yeah, you can see that 4, which is the minimum, okay, will be actually the error will be less than 1 over 4. Here the error will be less than 1 over 16 over 25. So what is greater, 1 over 4 or 1 over 16 over 45? 1 over 16 over 25 is greater because it is 25 over 16, and while that is only 1 over 4. So the error will be constrained more in case of LMOT as in case of repetition scheme. So what is the overall advantage? Overall advantage you can see is 4 over 16 over 25 because it is giving 4 gain, coding gain, it is giving 16 over 25. So 4 over 16 over 25 is 25 comes in the numerator, 25 into 400, 100 over 16. 16 8s 16 5s 80, 16 6 96, 6.25, approximately 6.25 times better coding gain is being given by LMOT over the repetition scheme. So for PAM 16 over 25, this translates LMOT scheme roughly a factor of 6 or greater than 6, actually 6.25 with the analysis. But because why this is better? Because LMOT is utilizing all the degrees of freedom in comparison to repetition, because repetition requires 2 symbol times to get 1 symbol, while in LMOT in 2 symbol times you are getting 2 symbols. Can read this up. Now let us try to extend our discussion for MIMO. So as I have told you that the transmit scheme, just as LMOT scheme or all the MISO schemes, they were designed for 3G. And those before the MISO you have SIMO. The SIMO, you know, all our antennas and radars and in navigation, and anyway where you have, even in wireless, if you have, for uplink, if your mobile has 1 antenna and the base station has L antenna, so all those cases are covered in SIMO. MISO cases, you can see they were 3G. But then came MIMO. So I told you many times that MIMO is the basic requirement for 4G systems. So in MIMO is multiple input, multiple output. And now you have two antennas, both at the transmitter as well as the receiver side. So that is why, you know, these mobiles are expensive. I went to buy a smartphone. I said, no, it must be compatible with 4G. So it must have two antennas at least. It's a huge price difference. So I couldn't find less than 15,000 because yes, you require another full-fledged transmitter chain and receive change. So you require double the cost. So the cheapest I was finding 8,000. Here it was 15,000. You know, 4G compatible mobile. Now let us see what happens in MIMO. Now we have two transmit and two receive antennas. So as shown in the figure. Now how many, if let us say the channel is really, so how many H are present? So in a MISO scheme, when you have two transmit in one single, you could see that you had L cross 1, 2 cross 1. You had two channel coefficients. But when you have two receive antennas, now you have four channel coefficients. And here we assume that the transmit antennas and the receive antennas, they are very far away. Okay? With respect to one another as well as with respect to transmit. And so there, you know, the fading gain from, let us say, from one antenna to the one antenna of the receiver and from the one antenna to the second antenna of the receiver, they are uncorrelated. Similarly, fading gain from the 2 to the 1 and the 2 to the 2 antenna, they are also mutually uncorrelated, as well as this H1 2 and H1 1 are also uncorrelated with H2 1 and H2 2. So all of them are four independently fading signal paths are present. This means maximum we can get a diversity gain of 4. Now let us apply the repetition scheme. No problem, just apply repetition here. No problem, we don't have to go to LM-Murthy and so much complex. Let us just apply simple repetition. Send one symbol from one antenna, keep the other antenna silent, and then repeat the same symbol from the second antenna, keeping the first antenna silent. In two consecutive symbol time. No need to send the symbol in some, you know, in some other in some other slot when the channel coherence time has been crossed and all that. No need, because here you are sending this same repetition to the second antenna. The second antenna channel coefficients are different, so no need to delay. If I send my X symbol, what is the receive signal? Now in the I means one antenna, the one receive antenna will have H11. All right. So the first receive antenna will get H11. Okay. So here he is using this one for the receive and this one for the transmit. First is for the receive, then the transmit, then W1 for the first receive. Then I2, the Y2 will be equal to H21, which means second receive, first transmit, and W2. This will be happening at time 1 and the second consecutive symbol times time 2. I will repeat the symbol and in that case again I will get Y1 okay, in the first antenna. So that will be equal to H12 because it was being sent from it is received at the first antenna, but it is sending from the second antenna now. H12 W1, this will be H22 plus W2. So in this case you can see that you are getting 2 plus 2, 4 different outputs. Now see, 4 different outputs have 4 different channel coefficients. Now you can very well apply the same you know, maximum ratio combining, you can say, or in other words what we were doing from the very beginning, you know, multiplying the receive signal by, you know, H mod over H conjugate, you know, receive Y is multiplied by H Hermitian over H mod. This we have done many times, from space-time codes to, you can say, rotational codes, repetition code, and then even from the very beginning this has been happening, H over H. Same thing you can see. So if you will assuming that, you know, we have a coherent scheme, so all the coefficients are known, so all the H will be multiplied with their conjugates, and you will have full-fledged H mod square available for all the channels, and hence you will have a 4-fold diversity gain. Right, very good. But here we have one problem. The problem is that All the time getting full diversity gain. 4 channels, 4 SN to the power L, 4 will be given, no problem. But there is one problem. The problem is that I'm not utilizing my degrees of freedom freely. Because why? Because you can see I am sending one symbol in 2 time. I am sending one data symbol in 2 symbol times. And you can at least see that I have 2 receive antennas. I can get actually 2 degrees of freedom per symbol. But here I am getting, you can see 1 over 2. It is 0.5 and I can get 2. So I'm not utilizing my degrees of freedom. So let us see all here apply LMOT scheme. Why don't we apply LMOT scheme? Or we say, oh, we apply LMOT scheme and we say, send 2 symbols. All right. The 2 antennas will receive. Then we again send the 2 symbols, but you know, one is minus conjugate, other is just conjugated. And again, I will get 2 different outputs. And you can see in this exercise, which is also in the course, that again, this will come out to be, 4 independent channels, and you will be getting this full-fledged diversity gain. All right. Because, LMOT is better than repetition. Okay, it not only gives you diversity gain, but you can also see that it is giving us it is utilizing degrees of freedom in a better way, because now you are sending 2 symbols in 2 symbol slots. So you are actually effectively sending 1 symbol once per symbol time. So you improved from 0.5 to 1, but still you are way behind the actual capacity, which is actually 2 per symbol time. You are actually now utilizing 1 per symbol time. Does it utilize? No, it not utilize, because now you have 2 degrees of freedom. So degrees of freedom, it is actually dimension of the received signal space. And in a channel with 2 transmit and a single receive antenna, this was equal to 1 for, yes, if I have 1 receive antenna, it was 1 per symbol time. And the repetition scheme was only half, while LMOT was utilizing it full if for MISO. Now, if we discuss for SIMO, single input MIMO, where a single input and multiple output, where we have L receive antennas. So I will say, oh, L receive, I might have my my dimensionality L, but actually you will see that dimensionality is still 1. Because why? Because yes, I have this much signal, but when I will be receiving this signal, how do I receive the signal? I have to do H into H mod, and when I will do H into H mod, you can see H into H mod, this is same L cross 1, L cross 1. This will be just H mod square. I will just one constant. I will just get 1 gain. All right. And we have seen this also, in the alternative view on the last lecture when I discussed in detail the error in the complex space and an alternative view of detection in a vector. You could see that all the other dimensions were noise, and only there is one dimension, which was this HH. Okay. So again, this is a 1-dimensional space, HX. It is not 2-dimensional space as in LMOT, because in LMOT you had 2 orthogonal channels, H1, H2, and another was the conjugate version. So again, for SIMO, it is again 1 symbol per time, degrees of freedom. It is actually 1 symbol per time, because you are potentially still not able to get 2 different orthogonal channels, even with SIMO. All right, now coming back. Now, coming back to our MISO scheme, 2 cross 2. All right. So there I am saying that I have actually potentially I can have 2 degrees of freedom per symbol time. What is it? Because I have 2 antennas, so I must be able to get 2 different symbols per symbol time. Now let us see how is this possible. So first of all, we write the channel. So now I'm receiving Y vector because I have 2 receivers. So this is H1, channel coefficient X1. This one X1 symbol. Let us say from some antenna. This is X2 from the second antenna. So what will be H1 will be the channel coefficients from the first antenna to the first and second antenna of the receiver. So Xj and Hj are the transmitted symbol and the vector of channel gain from transmit antenna J, so from transmit antenna 1 respectively. So this H, अब आप इसको जिस तरह you can write. So book is using different approaches. So let us use the approach that the book uses as he has defined here, this file approach, but it will change sometimes. So don't worry, we will be adapting as the books, but let us do one thing as the book has mentioned. So you can see that this H1 matrix, this will be actually containing H11, H21. What is H11? Channel coefficient at the first receive antenna from the first transmit. H21 symbol will be present in this H, which will be channel coefficient at the second receive antenna from 1. And what will be this one? This will be H12 at the first receiver from 2 and H22 at the second from 2. So these symbols will be present in this vector. So, vector, this is a vector, and this is also a vector. All right. So in this way, these are defined. Our vector is the receive signal, and C and yes, the noise, each noise W1 is 0 and not, because it is both in the I and the Q channels. Now he's saying as long as H1 and H2 are linearly independent. So what is the meaning? That what is linearly independent? In matrices all you have studied that if I have two columns, and both the columns you cannot have some scalar you multiply and that you can get the second column. There is no other term in this manner. We say those rows or those columns are linearly independent, and in this case they will be linearly independent because H1 is coming from one antenna, H2 is coming from another antenna to the other two antennas, and they are all really faded. They are all random numbers. They are completely different. Okay, they are linearly independent. So once they are linearly independent, the signal space dimension is 2. Okay, so I can very well, for this one, these are independent, so I can very well separate once I know the coefficient. So once I multiply by H1, I will just get X1 because H1, H2 will go 0. Then I will multiply by H2, I will just get X2 and then H1 will go 0. So I can separate with no problem. The signal space dimension is a signal from in its own direction with two receive antennas. The receiver can distinguish the two signals. Okay. Compared to there is an additional degree of freedom coming from space. So there is an additional degree of freedom because you have H1 and H2. Hence, you can get two symbols. Okay, in one slot. All right. So instead of LMOT where you are getting one symbol in one symbol time, you can get two symbols X1 and X2 in same symbol time. Figure 3.12 you can see here. This is figure 3.12. So you can see that you can see in the 1 cross 2, which is the SIMO channel. So you actually have just one because when you multiply H with H, HH with H, you will get just a one number. So you will have only one dimension. But in a 2 cross 2 channel, you have two dimensions, H1 and H2. All right, H1 and H2. I think he has made a mistake. This should be bold. H1 and H2 should be bold. I don't know why he has written it. This should be bold like this. I don't know. I think he has made a mistake. So you can correct this in the book. Achha. So we want. All right. So let us go further. This is what I was talking about. Now, so we have seen the LMOT is good, but when we go to a MISO scheme, LMOT is not able to utilize properly all degrees of freedom. So which scheme can properly utilize? So let us try to find that scheme. So a very simple scheme is the following. Transmit independent uncoded symbols over different antennas as well as over the different symbol times. Whoa, whoa. Now please see what is happening. What he is trying to say is that, let us say if we have a 2 cross 2. So if let us try, apply. He say send U1, U2. In the second slot, send U3, U4. No need to repeat. In different time slots, symbol time, in different antennas, send different symbols. This is what he is trying to say. Independent uncoded or no coding like LMUT, no coding. Right? No coding like rotational codes where you rotate the codes. No, nothing. Simple uncoded. Simply weird symbols are sent. 2 symbol times. Different antenna, everything is different. Okay? This is an example of a spatial multiplexing scheme. So this was the first scheme that was devised. Actually, this scheme was devised before 4G. So then it was incorporated. But these types of schemes, they required 4G. They must have multiple antennas at the receiver. So here now comes spatial multiplexing. So remember the words that we are studying. So we studied, time diversity, frequency diversity was studied a little bit. Then we saw the coding gain. Then we saw diversity gain. Okay. Now here we are actually seeing another thing, which is spatial multiplexing. So a new scheme where you are sending independent data streams are multiplexed in schemes in space. So everything is independent. You are just sending. This means you are fully utilizing your degrees of freedom. Your rate will be very, very high. But what is the drawback? So it was called VBLAST. So let's try to analyze this scheme. So we extend the derivation of the pairwise error probability 3.85. So you can see 3.85. This has already been driven. After a lot of mathematics, you are able to show that the probability of confusing space-time codes XA and XB was given as follows. And finally, we could show this as a determinant criteria. From this, we will extend that. So he says that if you use this exercise 3.19 and you extend 3.85 with NR receive antenna, in 3.85 it was one receive antenna. It was a MISO. Now for MIMO, you can see it will come out to be the same formula, but everything is same, but it will be to the power NR, where NR represents the number of antennas. This is same. You can see it is the lambda L, or the same lambda L before the eigenvalues of the difference matrix. So it was difference square. It was actually lambda square was for XA minus XB, XA minus XB Hermitian. But for single, it will be lambda L for only XA minus XB. So this property will hold that if I am sending a space-time code over multiple antennas, then probability of confusing will be this, no problem. We will use this scheme. If I have LMUT, another scheme, and I'm using multiple antennas, I will be using this formula, no problem. But what is our scheme, which we are VBLAST, which we are discussing this scheme? What is our scheme? Our scheme does not code across time. If you can remember, how was this scheme devised? What was this XA and XB? So if you go back in the last lecture, you can very well see how was this XA and XB. This was your XA and XB. So you can see XA and XB. This X was a L by N matrix, where N is the next symbol time where the coding is done. But here we have no coding. We are just sending symbols, we are not repeating them. This means our n is 1. We are not repeating. There is no time coding. There's no coding here. We are just barely sending the symbols. So our x will be just L by 1, not L by n. If L by n, then n is equal to 1. So you can see here that the difference that will come out will be, yes, this remains the same. All these things are right. But you can see here that this x is not L cross n. It is L cross 1. So I will be getting this thing, but with the difference that XA is not, this is same, no problem. You can see H was L cross 1 and this was 1 cross L, this H conjugate. There's no problem. I'm not saying H is the same. All right. Again, different channel coefficients. All right. But you can see that this XA and XB, they are different. They are not matrices anymore. They are actually vectors. XA minus XB. H into XA minus XB mod. So coming back. Yes. The block length is 1. The code words are two-dimensional vectors, XA and X. They are only vectors now. They are no more matrices. And the bond simplifies is 2. So this bond will simplify. Yes, this 2 will be here, no problem. All right. Yes, very good. Now, but you can see here that this will now change to this value. All right. Now, this requires some mathematics in order to come from this step to this step. Right. Once you add this step, then there is no problem, because you can see this is this will be less than this, because square goes here. This one is very, very small. So this is one is neglected for higher SNR. We have done this many times. So in other words, again, you can neglect, if you neglect this one, this becomes more smaller and this overall becomes greater. So it is always less than this thing. Square is square, 4 square goes in the numerator, square becomes 4. So at this point, there is no problem. You can go from here to here. But how can I drive here? Actually, for this, so I take the help of some of the previous lectures. So I'll try to, open up. So as we have done all of this in the previous lectures, just as sake of, I think I have got the other page. Yes. So this was our last lecture. We have done these things. Yes. So a little just to revise, if you could see here. So I shown these mathematics because many things were missing. Now here you can see what is my UA and what is my UB. Yes, UA is still effect. Probability of error is this. We have seen this many times. We have done this all the derivations. So you can see what is UA and what is UB. So UA is this and UB is this. All right. But remember here XA is not L cross N, rather it is actually L cross 1. And while this is 1 cross L, so 1 cross L into L cross N, this comes out to be this comes out to be 1 cross 1. All right. So actually what this comes out to be, the received symbol comes out to be a symbol. It is not a vector anymore. Again check, no problem. This is what? XA, which we know is not L cross, it is L cross 1. It is L cross 1. And what is this thing? We know it is the L cross 1, but H, this means is 1 cross L. So 1 cross L into L cross 1, this will become 1 cross 1. So this is now a symbol. Yes, but it is a symbol. Similarly, this is also a symbol. This is L cross 1 and this is 1 cross L. This becomes a symbol. Both are symbols. So no need to go into vector. You can just use the probability of error of scalars. All right. And we have done this. Again, you can go if you want interested. Many times. If you go in the book, we have done scalars and vectors. They act as the same form. Only the vector they become different. So we have seen for vector we have this UA minus UB, mod. So it becomes a scalar after this mod. But what is for scalar? We have many times symbol, just mod. Just find the difference between the symbols. Just find the difference between the symbols. Because now you have just symbols. So if you take this and so probability of error is this, all right? Remember this. Now for this you can see which type of mathematics I would be using here. Does anyone remember where we have used the error for symbol? This was for symbol. Even you could see the previous were also for symbol. Because once this totally became a symbol. अगर if I can find that, इसमें तो लंबा चौड़ा था. But this one will be for vectors. That I just trying to make a good point. Maybe we are able to explain it in a better way. Yes, Q of so the symbol error was A of H. In our case it is again UA minus UB is just the difference. But still some steps need to be done here. All right. Even if I take UA minus UB, but I have to solve that. UA minus UB needs to be solved. Even it is a symbol, no problem. UA minus UB is a symbol, but I have to solve that so that I cannot just apply this mathematics here. I was trying to get a shortcut, but actually at this point of time, it is the same. We have to, again, we will be applying this. Once we get this form, we have to, apply this, and then again it will be like this. Same thing, it comes out, no problem. But, this shortcut is not working and is asking us to go to the mathematics part. So, किधर चले गए? Yes. So for here you can see that actually we will be getting the symbol difference. All right. And the symbol difference that will be H, XA minus XB. इसको कैसे करेंगे? अच्छा, so let us try to use this one. All right. ये क्या हो गया? Yes. Now I think, can you see the notes? The previous notes. UA minus UB. All right. You can see that. All right. This I think you can see. I think everyone can see it
Yes, sir.
now. All right. So yes, I know this is no more a vector. This is just a symbol. Let us try to use this. If not, then I have to do the whole mathematics in the next section. Just I am trying to, let us see if I can get this shortcut. So you have UA and this is UV, and I know now they are no more vectors. They are just symbols. So I don't have to put this more double line. The single line is more than enough. All right. This is a symbol. This is also a symbol. So yes, this will be mod square. If I put under root, no problem. All right. So this will be 1 cross n. No, this will not be 1 cross n now, because now n is 1. So this will be 1 cross 1. This will be 1 cross 1. They will be just symbols. Okay, they will be just symbols. And after that, you have to apply eigenanalysis, but here there is no need to apply eigenanalysis. All right, so I think I was trying to apply some type of shortcut so that it could be solved easily, but again we are stuck, because here again you have a symbol. This is a symbol, no problem. This is also a symbol, 1 cross 1, 1 cross 1. But if you want to apply the approximations of q being less than e minus x square over 4 exponents, so that you get that thing, so you have to simplify this so that you get symbol terms. So if I multiply this with this conjugate, this will become xa minus x. It will become like this. But the difference is that this is 1 cross L, and this is actually L cross 1. L cross 1, 1 cross L. There are many ways of solving this, but I think I should put some notes. I cannot explain like this, that it becomes like this and this, and so it will become very difficult. I should have done some work. I thought that this could be done in a short way, so I will leave this at this point. I won't go how it is solved. It's not difficult. You have to do the certain steps. All right. You can open this. Remember, this is just a vector now, no problem. But this is a vector. This is L cross 1. This is a vector. But this is actually a scalar. This is also, but this is a vector. You can also make it a matrix, and you can do its eigenanalysis, or you can take its this scalar, multiply, and then solve separate, and then again you can do the same mathematics as you have done before. You can approximate this, e minus x squared over 4, 2, and this will become 4, and again the second things will come out. There are various ways of doing it. So I will see whether I should do it, or maybe I could give this to you in an assignment. But whatever, I cannot do this now because I don't have a camera, so I cannot show you live, and I have not made it notes. So let us assume that on solving this, okay, we can get this thing, which is x1 minus x2 mod square after a certain number of steps. So we can go further, and not to, we have just 5 minutes, all right, then attendance, so we can let us do as much as possible. So this you know, this proof, either it will be done by myself or I might give you in some assignment if I find it to be very interesting. So this comes, let us say this comes out to be like this. This step I've already explained. Now here you can see that the probability of confusing x1 and x2 comes out to be SNR2. Now please see, what is SNR2? What is the diversity gain? Is the diversity gain 4 or the diversity gain 2? Can anyone answer? What is the diversity gain here? It is 2. This means we are not getting the diversity gain of 4 as you are getting in repetition and LMOT over MIMO. For this V-BLAST or spatial multiplexing, when we are not repeating in time, you will get only 2 maximum, because we have only 2 different channels. So we can maximum get 2 diversity gain. So it gives a diversity gain of 2 because there is no coding across the transmit antennas. And what is this factor? This thing. Okay. This is similar to this factor, the determinant criteria. So you can see now here you can see that you had this determinant and its minimum value was making an effect. So here if we have, let us say, x1 and x2, let us say we have some scheme, we have some BPSK symbol, and so we have to see what is the, again the same thing, but it was different because here you find the determinant. Here you just have to find, remember x1 is a vector now, all right? X1, you can see it is L cross, not L cross n, it is L cross 1, it is just a vector. So 2 vectors, they are different. This is just L cross 1 vector, and you are taking its mod square, then another square. So you are just taking, you know, first symbol square plus second symbol square, under root cancel square, and then it's square, x1 square by x2 by x3 square, whole square. So one square cancel with 1 over under root, so it is just square. It is just like this thing. So it is analogous, similar, but it is still different because there you are determinant, here you don't have a determinant. Here you just have a norm of a vector, because you know there you have used determinant to find actually for a matrix, but here you just need a norm for a vector. So you can see here that compared to LMOT, V-BLAST has a smaller diversity gain, 2 in comparison to 1. But on the other hand, it uses full degrees of freedom. So its rate is greater. To see concretely, you can see if I use using BPSK symbol, in BPSK symbol, you can see you can send, if I just use BPSK, I have 2 symbols. So I'm sending 1 bit per symbol time. But because if I apply LMOT, then you know I'm sending 2 symbols in 2 time, or in other words, I am sending 2 bits in 2 time. I'm sending 1 bit in 1 time. Suppose we use BPSK symbols in, if I use BPSK with LMOT, I am sending 1 bit 1 per time. But if I use BPSK with spatial multiplexing, I am sending U1, U2. In other slot, I am sending U3, U4. So I am sending 2 symbols. I am sending 2 bits in 1 symbol time. So my rate will be 2 bits. Actually 2 bits per symbol, but he is writing this at 2 bits per second per hertz. So actually you can, you know, we can call our symbol as symbol per, as second per, because you can see what is a symbol. Symbol is something, you know, a signal. It takes some time. All right. So I am saying this much bits per symbol. So that is why it is bits per second, or second. And then you can also see that a symbol will be occupying some you know, some frequency. All right. So you cannot just send a symbol with, it has to be on some frequency. So it is per symbol, or in other words, you can say bits per second per hertz. So it is occupying some second as well as some frequency. So if I assume that the average transmit energy per symbol is normalized, same thing which I told you. Same thing. Remember how to normalize one? I told you how to make it 1, because in 1, for example, LMOT, it was 2a square. You divided by 2a square, so it became 1. It was 5b square. You remember in PAM I was just sending one symbol. That is why I divided by 5. If I was sending two symbols, PAM symbol, let us say, or LMOT, I would have to divide by 5b square plus 5b square. 10b square would have been the division point. So you have to divide it so that the normal energy comes out to be. So it is normalized as before. So we use 3.92. So the above equation, use this equation without it, let us say, is proof. And the worst case error probability of confusion, and he says that it comes out to be 4 SNR minus 2. So SNR minus 2 is SNR minus 2, but main thing will be what is x1 minus x2. That needs to be actually found out. But here remember that this will be some code, other code, and you will take the minimum of the difference. Okay. So again, that is present in my notes and I have not shared, so I will be sharing it in the next lecture. You will see that it comes out to be finally 4. So 464, it comes out to be 4 above in the numerator, and hence this will be driven. So we will leave this to the next lecture, and we will mark your attendances. So if you have any question, you can ask now. Any questions you can ask before I try to take your attendances? All right, no problem. I will take your attendance. So I think you can all see the attendance. So coming back here, I'll stop the recording so that recording becomes very large. So